the Earth would be a dead planet without the Moon. We underestimate how crucial a function our satellite plays in the survival of the Earth and its inhabitants. A bond that dates back to the moment of their formation binds the Earth and the Moon together in a very tight relationship. A few tens of millions of years ago, when the Earth was still a newborn, the surrounding space was filled of evil objects of all kinds, from tiny rock fragments to very enormous bodies, which scurried here and there attracted by the Sun and the numerous planets in formation. As a result, collisions were common and frequently resulted in significant changes to the size and appearance of the bodies involved. Theia, a massive protoplanet with the mass of Mars at the time, wound up passing directly over the young Earth because it chose a chaotic orbit around the Sun. A few kilometers per second was the pace at which Theia struck. The planetoid's iron core slid into the Earth's mantle until it fused with the Earth's core during the inelastic collision, which transformed almost all of the kinetic energy into heat. The part of Theia's mantle that was furthest from the planet was spared by the impact and continued on its course, but was disturbed by the planet's gravity and changed course, entering its orbit, where strong tidal forces smashed it into tiny fragments. 80% of Theia was entirely digested in a matter of hours, while the remaining 10% formed a disk of trash surrounding our planet. The disk finally contained gas, tiny particles, and molten rock, almost entirely components of the Earth's mantle, which is typically low in iron, due to the terrifying amount of heat that the collision's energy had produced. Rocks that appeared to be free of volatile substances were left behind after other light components evaporated and were lost in space, but as the Apollo missions subsequently showed, they still contained minute amounts of water. After that, the disk started to cool by radiating heat into space. The particles quickly hardened, leaving the Earth surrounded by a ring of rocks that reached up to 30,000 kilometers from its center. The rock fragments started to smash and aggregate, growing bigger and bigger, but the ideal location for aggregate formation was only beyond the so-called Roche limit, which is situated approximately 3 Earth radii away, where the tidal force of our planet was weakest. Beyond that point, the solid matter rapidly started to consolidate into larger and larger planetoids, which in a few thousand years gave shape and mass to one single celestial body, the Moon. The Moon is unquestionably a half-sister of our planet, if not a sister. However, in order to determine whether and to what extent this half-sister has impacted Earth's evolution, we must conduct a small thought experiment and picture the planet without it. What would happen to our world if the Moon didn't exist at all, or even if it weren't real? After all, only removing the first brick would cause the entire structure upon which the Earth-Moon system's history has been built to collapse, and then to vanish. What would have happened if Theia, which impacted Earth 4.5 billion years ago, had simply grazed it? First off, it's not hard to imagine what would have happened if the Moon had never formed. The Earth would have continued to revolve about itself at the same rate it did 4.5 billion years ago, when its day barely lasted 4 or 5 hours. The Moon itself, together with the enormous tides it generated, was responsible for slowing the Earth's rotation. How? Well, simply by creating friction on the bottom when the tides moved counterclockwise to the rotation. Would the onset of life have been possible with such a rapid rotation? Would you still believe that sophisticated life could have arisen if I told you that such a rotation would have encouraged the production of winds that would have traveled the Earth at a speed of at least 300 kilometers per hour? Maybe life would have survived nonetheless. The truth is that without the Moon, which at the time was 10 times closer to the Earth than it is now, our seas would have only been caressed by the incredibly weak tides produced by the Sun's gravitational pull. Not even close to being able to halt the rotation and lengthen the day to its present size. Additionally, they are unable to churn the ocean's water vigorously, which is a crucial task that biologists believe is required for the earliest cells to emerge on Earth to obtain the proper combination of building materials. In fact, it is thought that the tides were crucial in safeguarding and fostering the emergence of life on our planet, and that life can advance more rapidly and effectively in areas with favorable environmental factors that can trigger genetic selection. As biologists like to say, in reality, weak tides lead to delayed biological evolution, whereas powerful tides lead to rapid biological evolution. It is also generally recognized that one of the most crucial factors for long-term climatic stability is the inclination of a planet's rotation axis with respect to its orbital plane. Although the Earth's inclination is currently 23.44 degrees, which is unquestionably ideal, over time it may be significantly impacted by the gravitational perturbations of the other planets. Fortunately for us, the existence of a moon of this size can limit this change to a range of little over 2 degrees. Over the length of a 41,000-year cycle, the extreme values are roughly 22.1 and 24.5 degrees. However, even such a minor alteration has a significant impact on the climate. A larger tilt results in more harsh seasons, with hotter summers and colder winters, as the poles alternately point in the direction of the sun. Comparatively, the polar tilt of Mars, which is now and very coincidentally similar to that of the Earth, changes chaotically between 0 and 60 degrees during a period of around 10 million years. The enormous temperature fluctuations that can result from such a vast range would prevent any attempt by life to establish itself. Since entire ecosystems have been eliminated and the world has completely become arid, the effects on the red planet have been dramatic. Therefore, by ensuring long-term climate stability for the Earth, the Moon is crucial in maintaining the obliquity of our planet. The Earth's obliquity would fluctuate chaotically between 0 and 85 degrees on timescales of tens of millions of years. Without the Moon and with the current 24-hour rotation period, most likely, our planet would not have been able to enjoy the climatic continuity required for the emergence of complex life forms, and we would not be here right now to discuss it. But this is just the beginning of the misfortunes that would have befallen our planet if the Moon did not exist. The Earth would have experienced significantly more intense cosmic bombardment during several phases of its development if there hadn't been a gigantic, enormous natural satellite capable of drawing on itself a significant portion of large and small asteroids. In essence, the Moon has served as a shield for our planet and continues to do so, much like Jupiter shields the inner solar system from Kuiper Belt comet impacts. In addition, many astronomers believe that the Moon's tidal effect is what first triggered some of the Earth's crustal renewal processes, such as plate tectonics and the continent's ensuing drift. The seafloor would have remained completely barren and devoid of interesting chemistry if tectonics hadn't forced the rock plates to plunge under each other and then back up again in a process known as subduction. This would have meant, first and foremost, that life at the microbial level would have had much more difficulty establishing itself, while life above would have been completely prevented from doing so. And once more, the magnetic field itself must give credit to the Moon's gravitational influence. The magnetic field of the Earth surrounds us for tens of thousands of kilometers and has its origins more than 3,000 kilometers below our feet. It can be visualized as a shell that envelopes our world, and it can be represented by lines, referred to as lines of force, that radiate from the Earth's south pole and circle back to the North Pole. For life to exist on this planet, the magnetic field is a crucial element. The Earth is continuously shielded from the flow of solar particle flow by such a magnetic bubble. Our star is actually a massive thermonuclear furnace that continuously releases vast quantities of ionized solar plasma into space, known as the solar wind. After traveling for a few days, the solar wind eventually reaches the Earth. Upon impact, the solar wind is constrained by the Earth's magnetic field and is kept there in the magnetosphere, where it flows like river water around a bridge pillar. Which is fortunate because the influx of high-energy particles has the potential to destroy our atmosphere and harm living creatures' DNA. Now, it is almost certain that the so-called geodynamics, the action caused by the swift movement of enormous amounts of liquid ferrous material in the outer core of our planet, is where the Earth's magnetic field originated. The origin of the energy that has fed the geodynamics for billions of years and still doing so is a topic that is hotly contested. The most recent studies, however, imply that at least some of the required energy may originate from the moon, specifically from the mantle's deformation brought on by tidal processes. Strong currents are created in the exterior core, which is made up of a liquid iron alloy with extremely low viscosity as a result of the mechanical force that is given to the entire planet. Currents powerful enough to create the magnetic field of the Earth. The Earth's core would stop rotating and subsequently solidify if it weren't for the moon and its rotational energy exchange. The planet's magnetosphere would also disappear with the geodynamo now off, allowing the solar wind to entirely consume the atmosphere. Any water present on Earth's surface would evaporate in the absence of an atmosphere, and solar radiation would transform our planet into a desolate wasteland. Once more, Mars serves as the ideal illustration of such a planetary catastrophe. The red planet once had an atmosphere and oceans, just like the present-day Earth. However, its magnetic field started to wane and eventually vanished 4 billion years ago. And over the course of a few million years, the solar wind gradually removed its atmosphere and, as a result, its oceans. A gravitational influence on a planet's magnetic field that has been well documented for 2 of Jupiter's moons, Io and Europa, as well as for a substantial number of extrasolar planets. If our species had been able to emerge, the lack of the moon would have had one final and perhaps more catastrophic effect, this time of a psychological kind, in addition to all the missed gravitational impacts. In fact, I believe it is safe to say that the moon was a major factor in inspiring our species to turn its gaze toward the stars and to begin pondering the meaning of events that were taking place on Earth. Much later, the presence of a celestial body so close to us undoubtedly helped us to imagine taking the first tentative step toward the stars. What kind of future might space exploration have had if we hadn't been lured by the prospect of a destination that was within a few days' travel time? Would we have made the same technological investments? In my opinion, no. In conclusion, this universe would not have existed without the moon for a variety of good reasons, both with and without us. Additionally, this places severe statistical restrictions on the number of such planets in our galaxy and raises issues about the conditions that must be met for a planet to be successful in developing higher life forms. In conclusion, efforts that are designed to look for life among extrasolar planets must be directed taking into account the presence or absence of a massive satellite. Keep checking back for more fascinating films on science and astronomy, and don't forget to like, share, and subscribe to our channel.